Okay, so let's continue our discussion on fields. Okay, okay. So in the last lecture, we had introduced about splitting fields. So please go back to the previous lecture and get hold of the notion of splitting fields. Okay. So in some sense, it was the smaller, it was a field extension corresponding to some polynomial in the underlying field, which completely splits into linear factors over that extension. Okay. Now something which we had proved is the following, that if f of t is in ft is of degree n, then I know the degree of extension of k over f is at most n factorial if k over f is the splitting field of f. Recall, right? But we had actually went with an important fact went unnoticed in this, that this implies that k over f is a finite extension. What does this immediately mean? This means that the extension of splitting fields is an algebraic extension, is algebraic. Getting my point? So actually, an extension being algebraic, it seems to be very complicated, because the definition actually includes that every element must have some some minimal polynomial over f, some things like that. But actually what we see is that if we choose some fixed polynomial over f and take hold of the smallest field over which that polynomial itself splits, the extension is still algebraic in nature. Getting my point? Yeah. And one thing which we sort of introduced in the previous lecture was in some sense an important idea, that every with respect to every polynomial there exists a splitting field, and we are also given a certain type of a structure to that by adjoining the roots of that polynomial to the underlying field. But something I had also said, that we can actually, rather than talking about a splitting field, we can actually talk about the splitting field, and that is something which we would like to discuss here: uniqueness of splitting field. Okay, okay. See, now the proof of this theorem is to be kept in mind. The reason being, the tool which we use to prove the theorem is actually a very important tool and is often used to prove extensions being isomorphic. Because later we will also prove that when we have introduced the notion of normal extensions, I think I will be able to do it in this lecture itself, that normal extensions are also unique in nature, and there we will be using the same tool. And this tool is also in some sense very similar, though not that similar, but still in some sense theoretically it's very similar to the way we proved that algebraic closures are uniquely determined up to isomorphisms. Yeah, so our claim is the following, that let f be a field and let's say f of t is subpolynomial over f, then let, okay, so let me remove this, let k and k prime be the splitting fields, sorry, be splitting fields of ft over f. Okay, then what we want to claim is that then the extensions k over f and k prime over f are isomorphic. We are talking about them being isomorphic extensions. So what is meant by isomorphic extension? We have discussed this in the previous lecture. The two extensions said to be isomorphic if, that is, there exists some isomorphism phi from k to k prime is an isomorphism, right? With the further fact being, with, okay, wait a second, okay, oh, sorry, yeah, sorry, I opened the, sorry, right. So with right, so with phi restricted to f being the identity map. Okay, that is what we want to prove. Okay, proof. And as I said that, please just go through the proof in details, because this is actually a very important tool which we often use. Okay, what we introduce is the following: let L and L prime be algebraic closures of K and K prime respectively. Okay. So now observe that we have the following tower of extensions: L over K over F and L prime over K prime over F. Okay, then can we conclude this, that L and L prime are algebraic closures over F as well, over F? We can surely do that, right? Because we have concluded just before stating this theorem that splitting fields are actually algebraic extensions, right? So this is an algebraic extension, this is an algebraic extension. By definition of algebraic closures, this is an algebraic extension and this is also an algebraic extension. Therefore, this and this are algebraic extensions, and L and L prime are algebraically closed, so L is also an algebraic closure over F, right? Right. So therefore, yeah. So now we will understand why we have actually introduced the algebraic closures, because now by uniqueness of algebraic closures, we have proved this: there exists phi from L to L prime, which is an isomorphism, such that phi restricted to F is identity. Getting my point? Right. So the reason why we introduced this algebraic closure was to get hold of some isomorphism. But then observe that, so actually what we have is a map from here to here, this is my phi. So can't I try and restrict phi to K, okay, and talk about this specific map? Since phi is an isomorphism, phi is already injective, so phi restricted to some, some subset in some sense will also be, or in this case a subfield, will also be injective. The only fact to be taken care of is that phi is, the only fact to be taken care is that, okay, right? Yeah. So what we claim is the following. So only thing we require is surjectivity of the restricted map to K. So claim phi of K is K prime. Then this phi restricted to K, then phi restricted to K would be the required isomorphism. Would be the required isomorphism. Okay, let's see. Now what we already know is that K is the splitting field over F, right? Now, so what we know, that K is F adjoint the roots of small f. Okay, fine. Now if I can write f of x as a naught plus a1x, so on and so forth, till a n x to the power n, where each ai comes from f, then what should be phi of, or rather, then what is f of alpha I? So f of alpha is a naught plus a1 alpha I, so on and so forth, till a n alpha I to the power n, which is equal to 0, right? But then what is phi of f of alpha I? So it should be phi of a naught plus phi of a1 times phi of alpha I, and so on and so forth till phi of a n times phi of alpha I to the power n is equal to 0. But each of these ai comes from the underlying field, right? And phi restricted to the field is identity map. So it is nothing but a naught plus a1 phi of alpha I, so on and so forth till a n phi of alpha I to the power n equal to 0. What does this prove? This proves that phi of alpha I is also a root of f, and it is in L prime. This should be in L prime, right? Why? Because phi maps L to L prime. Getting my point, right? Is it clear for everyone? So phi of alpha I is a root in L prime, right? Now suppose the roots of f in L prime are denoted as, let's say, alpha 1 prime till alpha n prime. So in other words, these alpha 1 till alpha n are in some sort of a permutation of these alpha 1 primes till alpha n primes, in some sense, right? Therefore, for all I, what I actually have is that phi of alpha is the image of alpha is some alpha I prime. Okay, well, let's say alpha j prime. Okay, for some 1 less than equals to j less than equals to n. But what does this conclude? This concludes that phi of f adjoint alpha 1 till alpha n, this is actually contained in f adjoint alpha 1 prime till alpha n prime. What does this mean? This means that phi of k must be contained in k prime. But then observe that this whole argument can actually be applied once again by reversing the roles of k and k prime and taking phi inverse into consideration, right? So reverse the whole argument, okay, interchanging k and k prime, right, as phi and phi inverse play the same role. Getting my point? So what I'm actually trying to say is the following, that so what I can actually prove is the following, that phi inverse k prime should be contained in k. But that, what does that mean? That means that k prime must be contained in phi of k. Getting my point? So if this is 1 and this is 2, so it implies that k prime must be equals to phi of k, right? Therefore phi restricted to k is an isomorphism which is further restricted to f being the identity map. So phi is the required isomorphism between k and k prime, which is identity when restricted to f. Furthermore, what I said previously, what we conclude is that phi actually permutes the roots of f. Is it clear for everyone? Right. Fine. Now, what we want to do is to go one step further. What we did is the following till now, that have f, then in some sense I am not using ft once more because I need to have f into my notation, and I chose a polynomial from it. Then what I did is that I wanted to construct the smallest field over which ft splits completely into linear factors. Okay. But suppose what I do is that without talking about a single polynomial, I take a collection of polynomials. Let fit, let's say I is in some indexing set I. am not saying that it must be a finite set. I can talk about set over any indexing set, any collection of sets in ft. Okay. And I want to talk about a field, the smallest field over which each of these polynomials split. Getting my point? For example, let's say suppose I choose the polynomial x square minus 2 x square plus 1, okay, and I take this collection over qt, and I want to talk about the smallest field over which both of them split, right? So therefore the field must be the smallest field containing q, containing root 2 and containing I. So this must be the smallest field over which both x square minus 2 and x square plus 1 splits completely into linear factors. Getting my point? So we want to talk about such a field over which a certain collection of polynomials over the underlying field should split completely. In other words, I want to talk about the splitting field of a collection of polynomials and not just a single polynomial. And this actually brings us to the following definition. Let k over f be an algebraic extension. We say that k over f is normal if there exists a collection of polynomials fit I in I over f such that k is the splitting field of each fi. Getting my point? So this is the definition of a normal extension. Is it clear? Is it clear? Now observe furthermore, the way we deduce this fact is that let's say let us in some sense say that fi is some collection of polynomials is in ft. So can't I construct the normal extension over f which serves as the splitting field of this collection by just adjoining the roots of each fi? Won't that give me the required splitting field? I guess you can already observe that this actually does the same thing, right? Getting my point? Right. So is it clear for you? Right. Okay. Now let's get back to our discussion. So this is the definition of a normal extension, and this is an example of a normal extension which I just gave before. So q root 2i is a normal extension because q root 2 and I is an algebraic extension over q, and it actually is the splitting field of x square minus 2 and x square plus 1. Now observe the following. Again a very simple and trivial observation. Suppose I talk about this extension itself, q root 2i over q. Then as I said, and as we all know, that this is an algebraic extension, right? What more do we know from here? That any polynomial, or rather any element, suppose I choose from q, or specifically let's say alpha is equals to root 2 or iota, because if I have any other element than root 2 and iota, then that is actually an element over q itself. So that just gives us a trivial observation of what we are going to talk. But suppose alpha is either root 2 or I, then we know the minimal polynomial of root 2 over q is x square minus 2, and the minimal polynomial of I over q is x square plus 1. And to be able to observe this very carefully, that both of these minimal polynomials split completely over this normal extension. Getting my point? Is it clear for you? Fine. In other words, what I actually want to claim here is the following. So let me go to the new page. That let I will fill up the gaps in a bit, but so let me just serve it as an observation till now. Let k over f be an algebraic extension. Okay. Then for all alpha in k, the minimal polynomial, let's say m alpha over m alpha t in ft splits completely over k, implies that k over f is a normal extension, right? This is a very trivial observation, because why is it so? Because k is just a splitting field of a certain collection of polynomials from the underlying field, right? So k is immediately a normal extension. Getting my point? Getting my point? Okay. But my question is the converse true? Okay, can I say this? That is my question. That if I am given a normal extension, then can I say that every minimum, I mean, if I choose any arbitrary element from k, then the minimal polynomial of that element will split over k or not? That is my question. It might split over some higher field. So can I be sure of the fact that it will split over k itself? Getting my point? So this brings us to the following theorem. Okay. Theorem. Let k over f be an algebraic extension, then the following are equivalent, and this actually gives us a way to actually talk about normal extensions in a very simpler manner. Okay. Number one, k over f is normal. Okay. Number two, and this is a very important statement, you need to be understanding this very well, that if L and let's say if L is an algebraic closure of K, and phi from L to L is an F automorphism. What do I mean by an F automorphism? Also be quite relevant to this term. F automorphism means that this is an automorphism which restricted to F is identity. In other words, phi is the isomorphism between L and F as extensions, but they are the same extensions, so there is nothing very non-trivial talking about it. But the term F automorphism is important, so it's a map from L to L which restricted to F is the identity map. Clear? Okay, so then for every such F automorphism, this is what is important. For every such F automorphism, phi of K is equal to K. That is, phi maps K to itself. Getting my point? And the third point actually brings us our observation that for all alpha in K, the minimal polynomial m alpha t in Ft splits completely over K. Is it clear? Now say 3 over, I mean 3 implies 1 is immediate, right? So this is immediate, right? So let's talk about, let's say 1 implies 2, right? So what do I have? I have the hypothesis that K over F is normal, right? So let K over F be normal. Let Fix, so then I is in I in Fx. So I ordinarily always write T and X, but please don't get confused. That's just a habit. Okay, that is a sort of what I call a slip of my pen. Sorry, right? So be such that K is its splitting field. Okay, let L be an algebraic closure of K and phi from L to L be an F automorphism. Okay, what we want to prove is that phi of K is K, right? Now what we know about the structure of K, that K can be formed by adjoining the roots of all these polynomials Fi to capital F. That is something we know. Furthermore, we also know from the proof of the uniqueness of splitting fields that if alpha in L is a root of Fi, because after all L is an algebraic closure, is a root of Fi, then phi of alpha is also a root of Fi, right? What does this imply? That phi of K is contained in K. But then again our usual step, reverse the argument, using phi inverse. Then what we would be having, phi inverse of K is contained in K, which would say that K is contained in phi of K, and this immediately proves that phi of K must be K. Got it? Is it clear? Right. So what we want to prove now is 2 implies 3, and that is actually the trickiest proof in this you know, uh, equivalence statements. Let's see. So we are assuming 3, right? So 3 is being assumed. That is, if L is an algebraic closure of K, and phi is an F automorphism of L, then phi of K is K. This is what we have in our assumption already. Okay, so I'm going to the next page. Okay, now suppose let alpha be in K and m alpha be its minimal polynomial, be its minimal polynomial over F. Okay, So what we want to prove is that M alpha will split completely over K. Suppose not. Suppose M alpha of X does not split completely over K. Does not split completely over K. Okay. Is it clear? Fine. Yeah. So what we want to prove now is that so suppose the minimal polynomial does not split completely over K. Now what we have in our hand, okay, that is something which is important. Okay. So let me draw the structure first. So I have L, I've chosen an element from alpha, I mean K, I've chosen alpha from K, and this is F, so I am choosing the minimal polynomial of alpha in F, right? Okay. Yeah, but what we know that alpha is a root of its minimal polynomial. So at least one root of the minimal polynomial of alpha is in K, right? Now M alpha X has at least one root in K, that is alpha. Okay. Also M alpha of X splits completely over L because of being algebraic closure over L. Fine. Now you can think this to be over L. I can write M alpha of X as pi of say X minus alpha I is equals to 1 to N. Writing it as a product of the linear factors of all its roots, right? Yeah, so therefore alpha 1 till alpha n are in L, right? So with some sort of reiteration without loss of generality, I can choose alpha 1 to be alpha. Okay. Now some alpha I is not in K by our assumption, right? Which is something which we have assumed to come up to a contradiction in some sense. So let, without loss of generality or in some sense that by reiteration, alpha 2 be not in K. Okay. Is it clear? Getting my point? So let me just redraw the diagram. Okay, I already have the, okay, let me draw it in this way. So I have L over K over F, L over K over F. What do I have is that I have alpha in K and I have alpha 2 over L. This is something which we have, right? Right. Yeah. So how can we proceed from here? Okay. Let me think. Okay. Now observe the following. Now alpha 1 and alpha 2 have the same minimal polynomial, right? Have the same minimal polynomial over F. So the statement I'm going to write, you can take this as an exercise because this is a very easy, this consists of a very easy proof and it is very easy a concept that therefore there exists an isomorphism from F adjoint alpha 1 to F adjoint alpha 2, let's say phi, which maps alpha 1 to alpha 2. Okay, clear? So alpha 1 is my alpha. That is something which we have already written. Alpha 1 is my alpha. So it's alpha 1. Clear? Now what we can do? Now this phi can be extended to phi tilde, right? In L. Getting my point? Okay. So I have, so what do I have? I have now L from F alpha 1 phi to F alpha 2 L, and this is over F, this is over F. So I am extending phi to L, right? So phi and phi tilde will also be an F isomorphism, right? So what can we do from here? Right, right. But then phi tilde from L to L will be an F isomorphism, is an F isomorphism. What does this mean? This means that phi tilde of K must be equal to K by hypothesis, right? But alpha 1 is in K, right? Right? And phi tilde of alpha 1 must be equals to alpha 2, because phi tilde is just an extension of phi, right? So actually why I could write this is the fact that phi tilde of alpha 1 must be equals to phi of alpha 1 because of being an extension, and this is equals to alpha 2 by the definition of alpha. But this contradicts the fact that, repeat after me, that phi tilde of K must be equals to K. Why is it so? Because just go back to the picture we had drawn. Alpha 1 is in K and alpha 2 is not in K. So how can this be true? Getting my point? Right? Fine. So therefore, this is a contradiction. This is a contradiction, right? So we have our proof that the minimal polynomial of alpha should have split over K itself. You got my point? Is it clear for you? Okay. Yeah. So therefore, given an algebraic extension, uh, what we can try and check for it to be normal is that if I choose an arbitrary element from an extension, then whether the minimal polynomial of that element splits over K or not, right? So given K over F, an algebraic extension, and I choose an element from alpha from K. So if the minimal polynomial of alpha splits over K, then what we can conclude is that K over F is normal. Is it clear? Okay, fine. Now at this point I would ask you to go back to the way we had discussed about repeated roots. Okay, I do not remember whether I had discussed this in details or not, but with context I'll keep discussing about repeated roots, the notions of derivatives, in order to check whether there exists a repeated root or not. I'll do that, but as far as I remember, I think we had discussed about the existence of repeated roots. Okay, so I will be ending this lecture itself. In the next lecture, what we will be talking about is two specific extensions, rather only one specific extension is very important to be left, because we are not talking about Galois extension in this series. We'll talk about that in some next series of lectures. But what I actually wanted to prove, or rather wanted to talk about, is what we call a separable extension and perfect fields. This is something which we will be doing in the next lecture, but I'm just giving the definition of separable extension for now, rather separable polynomials. Okay, let f is in fx, then we say f is separable if f has no repeated roots in any field extension over f. And the best way to check that whether it has whether it has any repeated root or no repeated root in any field extension, what we can do, repeat with me, just check in the algebraic closure of f, because we are sure that over the algebraic closure it will completely split into linear factors, and that is the best place where we can check about the existence of repeated roots or not. So check in the algebraic closure of. Fine. So the next lecture, our goal will be to talk about separable polynomials and separable extensions in more details. We will talk about perfect fields, and I'll also talk about briefly in terms of repeated roots, existence of repeated roots of polynomials, because that is in some sense required. I don't remember whether we had discussed this previously or not, because in the series on, the series of lectures on rings, I discussed multiple things. So in some sense I have just forgotten whether I did discuss repeated roots or not. I'll just verify it once, but still we'll talk about repeated roots as much as we require in this context, and then we'll end this series. Got it, everyone? So meet you guys in the next lecture.